So far we have been discussing sets, cross products, relations, functions, graphs. They are all in the context of finite sets. Often, many interesting sets in computer science, we shall list a couple of them shortly, they are all infinite in nature. So that brings the theory of infinite sets into our lecture series. Let's discuss that. Look at this question. How many computational problems are there? So, problems such as say linear search or binary search, so in general search, and similarly sorting, shortest path, and many more, primality, determinant of a matrix, permanent of a matrix, they are all computational problems. Like this, we want to know how many such problems exist. Can we count? Can we say there are 100 problems? There are finitely many? Or is this infinite in nature? That's one. Say you fix a problem, say search. Then you ask how many different inputs are possible. So to this search problem, what does it take as an input? A comma x. So this could be an integer array. Now we want to know, is x in A or not? So now how many different A comma x are possible? So questions like this is what we are interested in as part of this, and you would be surprised that many interesting sets that we come across in computer science are infinite in nature. So it makes us to study the theory of infinite sets. Okay, let's focus on this. Something that you know already are the natural numbers. So we don't differentiate natural numbers and whole numbers. So we say it starts from 0 and so on. Then you must have seen real numbers. So we'll keep these two as something like base sets, and we explore other sets. Okay. There are other interesting questions that we ask. Can we compare two infinite sets? Can you say one set is larger than the other? And things like that. Because for a finite set, you just have to look at the cardinality and say this set has got 10 elements, the other set has got 15 elements, so the one which has 15 elements is larger than the other. But in the context of infinite sets, you may not be able to give a precise count, but can you still establish a relationship? And among infinite sets, this infinite set has more elements than the other. So things like that we shall explore. And all that has got applications in the field of computer science. And I've just listed two fundamental problems. And you see that these two fundamental problems are infinite in nature. We shall prove them shortly. Okay. Let's revisit the theory of functions and learn some material, and which we will use it here. So we say cardinality of A equals cardinality of B if and only if there exists a bijection from the set A to B. is this telling us? If you have two sets, say A and B, and this has got say n elements, and even this has got n elements, if they are of same cardinality, then the simplest mapping that you can think of is you map A1 to B1, in general AI to BI. So f of AI is mapped to BI. This is a function which is one to one and onto, and you see that they are bijective. Converse, suppose the function is bijective, which means for each of them there is an image, because by definition each of them should have an image. No two maps to same because of one-to-one property, and which means for each of them the image is different. Similarly, it's onto, for each of them there is a pre-image, so that ensures and no element is mapped to more than one by function definition, and as well as one to one. So now it tells you that when you have a bijective map, then it must be the case that the cardinality of A and B must be same. Now can we take this note to the theory of infinite sets? So please note, if you could establish a bijection between two sets, whether it is finite or infinite, so now this has got so many elements and this has got so many elements, we don't know, it could be infinite. But all that we know is each map is unique, meaning an element here maps to exactly one element here, and no two maps to same, and because of one-to-one property. Similarly, no element here is left out because of onto property, and if you take an element here, there exists unique image. So now that tells you that they are of same cardinality. So if there exists a bijection from A to B, this implies that cardinality of A equals cardinality of B. And if it is a finite set, we can say this number is say 25, this number is say 25, or if it is more, what is that number? But we won't be able to give you a precise number, but we are still able to compare the two sets, that they are of same cardinality. Both are infinite in nature, but both infinite sets are of same cardinality. See, the point is, can we compare them? It is not the case that you should always give a precise estimate whenever you do the comparison. No. As long as you are able to compare, yes, there is a purpose and there are applications that demand that. And very similar to what we did before, if there exists an injection, what is an injection? Injection is one to one. If there exists an injection from A to B, then you can say that codomain should have more. Cardinality of A is this. On the similar line, if there exists a subjection is onto, which means cardinality of A is greater than or equal to cardinality of B. And this itself is a lot in the theory of infinite sets when we want to compare two infinite sets. So let's look at some basic sets, something that is familiar to you, and compare their cardinalities, and let's take it to the next stage. There are a couple of things that one should note. When we study in the context of finite sets, often intuition and logic, they go hand in hand. You intuitively think the set is finite, and you intuitively think the set A is larger than B, and you see that the logic is also kind of matching your thought process. You try establishing through a formal argument to say that my intuition is indeed right. Here is a logic, formal argument is precisely logic. Here is an argument which tells you that A and B are of same cardinality, or A is larger than B, and so on. But often, this intuition to logic may not work all the time in the context of theory of infinite sets. Intuitively, you may think both are of same cardinality, but logic fails. Or logic tells you something else. Logic tells you that one set is larger than other set. But ultimately, it is the logic that wins, so one has to go by the logic. One has to go by a formal argument. What does the formal argument says? If the formal argument is saying they are of different cardinality, then intuition is weak. One has to strengthen the intuition to understand where did we go wrong, and is our imagination or is our understanding of the abstraction right, and so on. Okay, and let's explore all that in a short while. Let us compare the cardinalities of the natural numbers and the set of integers. So on one side you have 0, 1, 2 and so on. This is the set of natural numbers. On the other side, the set of integers, 0, 1, 2 on this side -1, -2, like this. Now, intuitively, if you see, it looks like n is a strict subset. It's only an intuition. N is a strict subset of this. Now, logic also tells you that yes, n is a strict subset because there are other elements over here. Now, with this you may conclude that cardinality of n is strictly less than cardinality of I. This is what you will conclude if you just follow the intuition. But logic says something else. So logic says they are of same cardinality, meaning I can establish a bijection. I can establish one-to-one correspondence between elements of n and elements of I. There exists a unique mapping between pair of elements, one in n, another in I. So intuitively you think this is like positive natural numbers and this is like negative natural numbers. In some sense, this is 2 times I and n is a strict subset. Therefore, I has got larger cardinality. But here is a bijection. So what we will do, we will arrange I like this: 0, 1, 2, 3 on this side, -1, -2 on this side. Just for my convenience, I am listing like this so that it's easy to visualize the mapping. The natural numbers, let me list like this: 0, 2, 4, 6. Even natural numbers on this side, odd natural numbers on this side. Now here is a mapping. So 0 is mapped to 0 and 1 is mapped to 2, 2 is mapped to 4, 3 is mapped to 6, like that it goes. then minus 1 is mapped to 1, and minus 2 is mapped to 3, then minus 3 is mapped to 5, like that it goes. Fine. Now you see that if you take an element and from this side they are all mapped to even natural numbers. If you take an element from here, they are all mapped to odd natural numbers. Fine. Now this is interesting. So this map tells you that each of them has got a unique mapping and vice versa. And no two elements here map to an element here. Similarly, no two elements map to an element here. Correct? So given this, now you see that there exists a bijection between the set of natural numbers and this. So here is a function from n to I that tells you, or I to n, doesn't matter, n to I or I to n, which is bijective, which implies that cardinality of n is same as cardinality of I. Both are infinite. Both are infinite in nature, but both are of same cardinality. So we may not be able to give you a precise number. We are still in infinite zone, but they are of same cardinality. So the other interesting part is this. One can also establish a formal map, say f of x. So the function is from I to n. So one can establish a formal map from I to n. You see that the mapping is like this. F of 0 goes to 0, correct? And you say f of x, suppose x is 1, 2, 3 and so on. Suppose x is positive, then the function says 1 is going to 2, 2 is going to 4, which means it is mapping to 2x. And what is the value of f of x if x is negative, x is less than 0? It says 1 is mapped to 1 and 2 is mapped to 3, and if you leave the negative sign, 2 is going to 3, 3 is going to 5 and 4 is going to 7, then which means it is 2 into mod. When I use mod, you will only get the absolute value, that minus 1. So now you see that if it is minus 1, this will return 1, then it is 2 minus 1, 1. If it is minus 2, then this will return 2, 2 into 2, 4, 4 minus 1, 3. If it is minus 3, this will return 3, 6 minus 1, 5. And that's precisely the mapping. And you can see that this map is 1 to 1 and on 2. Therefore, f is bijective and these two have same cardinality. Now what we will do, we will take our underlying set to be, say, the set of natural numbers or set of integers. And we talk about integer arrays of size, say, 10, 100, 20 and so on. Now it makes sense to ask how many different integer arrays are possible. Can we count? Can we list them? Such questions we shall look at next.